Good afternoon, good morning, good night, everybody. So today we have the pleasure to have here a talk by Professor Yuanqing Cheng from Beihang University, China here. So Carolina will be the session chair. And so I give the floor to Carolina to do the presentation of Yuanqing Cheng. So, I also would like to thank again Yuanqing Cheng to accept our invitation to give this talk today. Now is more than midnight in Beijing, so of Saturday. So, Carolina, the floor is.
So it's my great pleasure to introduce Professor Yuanqing Cheng, who has kindly agreed to speak to us on the subject of a reliable and low power design for STT-MRAM. Professor Yuanqing Cheng has an extensive list of publications in physical design and reliable of 3D IC, low power, and reliable design of emergency semiconductor technologies, especially on STT RAM. He got his PhD degree from the Institute of Computing Technology, Chinese Academy of Science, and he did his postdoc at CNRS Lille, France. And he is currently a professor at the Beihang University, China. He is a IEEE and CF senior member, and he is part of DATE, ISCAD, VLSOC technical committees. Thank you very much again for accepting our invitation.
Okay, thank you very much for the kind invitation and your very kind introduction. And so I'm also very glad to be here to introduce my research work in past several years on the reliable and the low power design for STM RAM. And I hope the audience can be interested in my research topic. If you have any questions, please just use the dashboard to leave your message, or you can also open your mic to interrupt my speak freely. First of all, I would like to introduce Beihang University. Beihang University is in Beijing, and Beijing is located here in China. Beihang University has a main campus located in Zhongguancun Science Park in Haidian District, Beijing. And we also have another two campuses. One is in Shahe, and which is 27 kilometers away from the main campus, and another one in the south of Beijing. In Beihang University, we have many kinds of academic programs for undergraduate students, master students, and doctor students. And we have over 2,000 faculty members and more than 30 schools. As for the discipline ranking, according to Shanghai ranking, the global ranking of academic subjects 2017, the aerospace engineering was ranked the second place worldwide, and there are also some other disciplines that was ranked as top 50 worldwide. Now, I would like to introduce myself briefly, and I got my PhD degree from CASS, China, and then spent my postdoc research in France, and also I visited UCSB as a visiting scholar during 2015 and 2016. Now, I'm an assistant professor in Beihang University. Today, in my talk, because the title of my talk is about the low power and reliable design for STT-MRAM, considering that maybe some audience are not very familiar with the STT-MRAM RAM, so I would like to present some preliminaries of Spintronics and the STT-MRAM RAM. After that, I will introduce my research work on the reliable and low power design for STT-MRAM RAM in past several years in different aspects. Finally, I would have an outlook of reliable and low power design for STT-MRAM RAM. As the technology node shrinks down, and we have many challenges, but also have many opportunities in the post-Moore's era. And as we see in this big picture, we have a very complex memory hierarchy in modern computers. For example, we may have a L1 or L2 cache, or even last level cache on chip. Off chip, we have a large capacity main memory. After that, in the lowest level is the hard disk or SSD disk. As the as we see in this picture, that the on-chip cache capacity increases to meet the ever increasing big data processing ability required for the modern applications. But the SRAM-based cache system has very severe leakage power, so it is called the power wall problem. At the same time, due to the off-chip memory access, we have the memory wall. It means that we have to spend a lot of time for the main memory access that is off-chip, which may degrade the computing performance very severely. To deal with the power wall and memory wall problems, we have many emerging memory technologies that can work together with the conventional CMOS technology to deal with these challenges, such like the resistive RAM and magnetic RAM or phase change memory. And to be work together with the CMOS technology, we can use the 3D integration, which can combine all disparate semiconductor technologies onto a single chip, so that we can take the full potentials of different semiconductor technologies to meet the ever increasing computing performance requirement. Today, my talk will focus on the MRAM. The Spintronics is the theoretical foundation for the MRAM or the Spintronic magnetic RAM. And this the Spintronic theory was founded by Professor Albert Burt and Peter Greenberg, who won the Nobel Prize in Physics 2007. They discovered the giant magnetoresistance phenomenon that laid the foundation of the Spintronics. As we saw in this figure, they observed that for the ferromagnet materials, and on the two ends of a stack, they can have different kinds of magnetization. If the two ferromagnet materials has the same magnetization, they can have a low resistance. Otherwise, they can have high resistance. With the difference in the resistance, we can store 1 bit in a memory cell. And this is the working principle of magnetic RAM. And this giant magnetoresistance is not based on the conventional charge property of the electron. It is based on the spin property of the electron. In fact, before the appearance of STT-MRAM, we have already used the giant magnetoresistivity phenomenon in the hard drive. And we used the GMR to embed it in the hard drive to sense the database stored on the hard drive. We can inject a current to generate a magnetic field. And depending on the data bit stored on the hard drive, the very small nanomagnet may have different magnetizations. For example, for data 1, it has one magnetization direction. For the data 0, it has the reverse magnetization direction. So depending on the magnetic field direction, we can read out the data stored on the hard drive. It is 0 or 1. With this resistive property, we can construct a stacking structure that is composed of magnesium oxide and other materials sandwiched around the magnesium oxide. This stacking structure is called the magneto-tunnel junction, which is the core component of STT-MRAM. As we can see in the middle figure, it has two distinctive resistance. The high resistance is called the anti-parallel state of the MTG, and the low resistance is called the parallel state of the MTG. For the different high and low resistance, we can approach a very high TMR ratio. It means it is the metric measures the difference of the high resistance and the low resistance. The higher the difference it is, the much more easier we can distinguish the data 1 from data 0. And on the other hand, because of the integration density increases sharply as we approaches the very deep submicron region, and on-chip cache capacity also increases very significantly. The leakage power is a big problem, as we mentioned before, and so the STT-MRAM can play a very important role as on-chip cache to replace the conventional CMOS-based SRAM. The magnetic RAM research and development was started from as early as 1996. For example, in 1996, a DARPA program that was operated by MIT, Honeywell, Motorola, and IBM, their research direction is to develop the magnetic random access memory. But in that period, the MRAM is what's called the toggle MRAM. It means that just let's look at the right figure. There are two orthogonal metal lines, and they can be injected with the different current in orthogonal directions. Because we know that the current can generate a magnetic field around the metal lines, this magnetic field can switch the magnetization direction of the MTG. So we can use this effect to change the data stored in the MTG. But it also has some drawbacks. First of all, the magnetic field may interfere with other MTGs. That means, for example, we want to change MTG 1, and at the same time, we can erroneously change another MTG, such as MTG 2. To avoid this kind of problem and to further improve the scalability of a magnetic RAM, the current induced spintronic RAM was introduced. Through this, it is called the STT-MRAM RAM, and STT-MRAM RAM was switched with the injected currents instead of the magnetic field, because the current can be generated within the circuits on chip, so we can obtain very high integration density and can eliminate the magnetic field interference problems in the turbo MRAM. That's why STT-MRAM STT-MRAM attracted enormous attentions from both industry and academia. This figure shows the typical cell structure of a STT-MRAM. It is called the 1 MTG and 1 MOS transistor structure. And by injecting the current through the MRAM cell, we can change the free layer magnetization. And if the magnetization of the free layer is the same as the reference layer, because the magnetization direction of the reference layer cannot be changed, it is fixed. We can only change the magnetization of free layer. If they are the same, this MTG has low resistance, otherwise it has high resistance. For example, we can denote the high resistance as theta 1 and another state, the parallel state, as the theta 0. Then we can implement to store the data in the MTG. In the first generation of STT-MRAM, the magnetization was in the plane that is the same as the free layer and the reference layer. It is called the in-plane STT-MRAM. It was built with the ship anisotropy effect. But this kind of MTG has very poor scalability as the technology node shrinks down. So to improve the scalability, the perpendicular STT-MRAM was proposed. In this kind of MTG, the magnetization is perpendicular to the STT-MRAM plane, or is perpendicular to the free layer and reference layer, as shown in the right figure. So my research work will focus on the perpendicular STT-MRAM because it can be more easily integrated with the more advanced CMOS transistor technology. Compared with other memory technologies like flash, phase change memory, MRAM has its own characteristics and also many unique advantages. For example, it has a faster read and write speed compared to flash memory and has very high read and write endurance. Also, the data retention time is more than 10 years. That can be classified as a kind of non-volatile memory. The capacity and density, although it cannot compete with the flash memory, but it is much higher than the SRAM memory. That's why the STT-MRAM can be used as the on-chip cache to replace the SRAM cache on chip. Now let's look at some very interesting problems involved for the thermal-aware reliable design for STT-MRAM. In our research, we observe a very interesting phenomenon, that is the TMR, or the high and low resistance ratio, varies with the temperature. As shown in the left figure, we can observe that the TMR decreases with the temperature because we use the difference of high resistance and low resistance to sense the MTG cell such that we can read out the data stored in the MTG. If the TMR is very small, it implies that it will be very difficult to read the data in the MTG. So we try to analyze the temperature impact on the read reliability and write reliability of the STT-MRAM, and look at what is the implication for STT-MRAM designers. We may have to pay attention to the thermal effect so that we can make our MRAM chip more robust and more reliable after fabrication. We used model developed flow to develop a Verilog A model for our circuit simulation. In fact, before our research, there were some other models developed by several institutions or universities, but usually they do not consider the thermal effect in their device model. So we used some formulas to characterize the thermal effect and embed the thermal effect in the device model. With as shown in the right figure, we can use this model to calculate the different TMRs in different temperatures. And through the iteration, we can make our device model converge to a steady state so that it can generate the final values of theta and phi. That's the very important parameters of the MTG device. By integrating the thermal effect into our MTG device model, and we can use it to evaluate the thermal impact on STT-MRAM memory access behaviors. But before we can perform our circuit simulations, we have to validate our result. This is the validation by comparing our simulation data with the experimental measurements published on IEDM conference. From this figure, we can observe that our thermal-aware device model coincides very well with the measured data from the fabricate devices. That also validates our thermal model. Then we evaluate the read and write behaviors of the STT-MRAM. In the left part of this slide, it is the thin circuit structure of the STT-MRAM. And this is the 1T1MTG cell structure. Usually, we resort a reference cell that can be composed of the parallel high resistance MTG and low resistance MTG. They worked together to generate a reference current. And when we read the 1T1 MTG cell, we also inject a current through the memory cell. By comparing the current through the memory cell and the reference current, or compare the voltages on the two branches, we can distinguish, or we can tell what data are stored in the MTG cells. On the right side of this slide, it is the right circuit of STM RAM, and we can inject the current through the MTG to change the magnetization of MTG device so that we can write a 0 or 1 into this cell. The MTG parameters we used in our simulations is shown in this table. Now let's look at the simulation results. From this figure, we can observe the read zero latency increases as the temperature increases. So it means that to read the data, we have to spend more time to stable the readout signals. It also means that it is more difficult to read out the data in the high temperature. This is because the TMR ratio decreases in the high temperature. This is similar for the case of reading data 1. So from these simulations, we can observe that the read margins, that is the metric as the measurement of how easy we can read out the data. And in the high temperature, the read margin shrinks so that it will be more difficult to read the data stored in MTG. And the read energy also increases because we also spend much more time to read out the data. That also results in high read energy. Except for the thermal variations in the environment, in the fabrication process, there are also some process variations. So we also combined the process variations with thermal effect to evaluate that what is the thermal impact on the read reliability of STM RAM. As shown in the right part of this slide, we can observe that as the temperature increases, the overlapping between the data 0 readout voltage distribution and the data 1 readout voltage distribution, the overlap between the two parts becomes larger in the high temperature. This means that we will have a high probability to read erroneous data from the MTG. For example, sometimes we would like to read out 0 from the MTG. But in fact, due to the overlapping in this region, we may erroneously read out as data 1. So in the left bottom side of the slide, we can clearly see the increasing error rate for the read operations in different temperatures. This is the very important issue that needed to be resolved. And this overlapping is also called the read disturbance. That means that we erroneously read out the wrong data in high temperature. And as the temperature increases, the read disturbance also becomes more severe. As for the write operation, because the increased temperature can reduce the thermal stability, so we can switch the MTG state more easily. That is why the write performance increases with the temperature, and the write error rate decreases. So the main problem in the high temperature is the read disturbance. So in the next step, we try to use some circuit optimizations to deal with this read disturbance problem. Before we talk about the circuit design, we also very interested in the model scaling in our thermal analysis. That means that how will the thermal effect in the ultra deep submicron technology node, for example, when the technology node shrinks down to 1/10 nanometer, such like 11 nanometer or even sub 10 nanometer. We also use the similar developed flow to develop our Verilog A model that is calibrated with the measurements of the fabrication prototype. With this model, we evaluate the read and the write behavior. And we can observe that in the 1x nanometer technology node, the MTG resistance increases sharply, and so the read current becomes much more smaller than the case in the, for example, 45 nanometer or 32 nanometer. But the read performance also decreases with the temperature, and the read energy decreases with the temperature as well. So the read disturbance is still a very big problem in the 1x nanometer region. As for the error rate, we can clearly observe that as the temperature increases, the error rate also increases in 1x nanometer technology node. So to deal with this problem, we proposed a body biasing sensing amplifier design. In the memory array, we use the feedback mechanism that is shown in the middle of this slide. We connect the body terminal of the sensing transistor to the data branch to form a feedback loop that can mitigate or anti-effect the thermal issues of the MTG. That means if the temperature increases, we can give a negative feedback that can enlarge the difference between the sensing data voltage and the reference voltage. The simulation results on the right of this slide clearly shows that we can enlarge the sensing margin very effectively compared to the normal sensing amplifier design. From this evaluation result, we can also observe clearly in the left bottom figure that as the when we use the body biasing feedback sensing amplifier design, the error rate can be reduced effectively. It is because we can improve the read margin very effectively. After we investigate the thermal impact on the STT-MRAM design, we also find another very interesting problem is that because the TMR decreases with the temperature and it has a very severe read disturbance problem. But at the same time, the TMR or thermal stability decreases, making it much easier to write data into the MTG. observe that there is a significant thermal gradient on chip, as shown in the right figure. This is the multi-core processor. We use the hot spot to simulate the on-chip temperature variations. We can observe that the thermal gradient can be as much as 30 degrees. So can we make a trade-off between the reliability and the performance? It means that we can try to exploit the thermal property of MTG device to improve the reliability of cache access, but at the same time, we can also seek the opportunity to improve the cache access performance as well. This is our adaptive thermal-aware ECC scheme for the reliable STT-MRAM design. As we mentioned before, with the temperature increase, the write and the read latency approaches to each other, and all the read current and write current approaches. This is the parameter we used in our simulations. And through this, the probability theory, we can derive the bit error rate in our STT-MRAM chip. For example, we calculate the read disturbance probabilities in different temperatures. And we also calculate the 2-bit error probability and the 3-bit error probability. From this table, we can see the error rate changes. The error rate changes significantly in different temperature. So the motivation of our work is that in the hot region, the error rate may be very high. So we have to use the stronger error correction code, or the ECC. The ECC scheme is used to protect the memory cell. And if the cell was read out erroneously, we can use the ECC code to correct it and recover the correct data. In the hot region, because of severe read disturbance, we may need a stronger ECC code. And in the cool region, maybe we can use the weaker ECC code. Because the stronger ECC code, it has larger area overhead and longer coding and decoding latency. Now let's look at our architecture design. This is the typical multi-core platform. We have four microprocessors each side. Among the 8 processors are many different cache banks. They may lie in the hot region or in the cool region. To evaluate the cache bank temperature, we use a linear approximation. We assume that there are many thermal sensors embedded on chip to sense the microprocessor temperature. In fact, these embedded sensors have been employed widely in the advanced Intel or AMD microprocessors. By evaluate the temperature distribution on chip, and we can assign different ECC code to different cache banks. For example, we can assign the core region cache banks with SEC-DED error correction code. It means it has the single error correction and the double error detection ability. Because this is the weak ECC scheme, so it can only occupy one cache line in a cache site. And in this case, we assume that our cache set has 8 cache lines, and among the 8 cache lines, 7 of them store the useful data, and the last one store the ECC code. And in the hot region, because we have higher error rate, we need the double error correction and triple error detection code. This is the stronger ECC code, but it also has larger storage overhead. So in this case, we have to allocate two cache lines to store the ECC code. But notice that with the applications run on different microprocessors, and the workload changes changes with time. So the temperature distribution on chip may also change with time, and we have to propose a dynamic ECC conversion scheme. Because, for example, in some time, the core region may change into the hot region due to the temperature changes on chip. What ECC scheme is used in this cache bank? So if we want to convert the DEC TD ECC, which is a stronger ECC scheme, to a weaker SEC-DD ECC scheme, and we can resort to this bank coding table to convert this ECC code. Because we convert from a stronger ECC to a weaker ECC scheme, we can have more free space in the converted cache lines. Just like in the left side, we must use 2 cache lines to support the stronger ECC. After the conversion, we only use 1 cache line to store the ECC code. So we have another cache line that is free now to store the useful data. And with the similar conversion procedure, we can convert the weaker SEC-DD ECC scheme to the stronger DC-TD ECC scheme. But in this case, we have to evict 1 cache line so that we can use 2 cache lines to store the ECC code. This is some experimental results, and our scheme can improve the performance by 4.1% and 3.6% on different kinds of benchmarks. That is the integer benchmarks and floating point benchmarks. These performance improvements are due to the low decoding and coding latency in the core region because of the weaker ECC code. At the same time, because in the core region, we only need 1 cache line to store the ECC. In fact, we have a higher effective cache capacity compared to the conservative design that is always use the stronger ECC scheme to protect the data on chip. At the same time, we can also achieve the energy improvements that is up to 10%, and especially in the core region, it is effectively enlarged the cache capacity, and so we can reduce the off-chip main memory access very effectively. That is the reason why we can save the energy. Now, I will introduce the reliable design considering the dielectric breakdown problem. In the STT-MRAM cache design, we have one scenario that due to the emergence of the edge computing and ultra-low power design, we may require a total non-volatile microprocessor. That is, the memory in this kind of processor are all non-volatile memories to achieve the ultra-low power design requirement. In this case, we have to use the STT-MRAM to build the total cache, the whole cache hierarchy to save the energy. But pay attention to that for the STT-MRAM as the on-chip cache, it suffers from the very intensive data accesses. And these very intensive data accesses may cause the breakdown, dielectric breakdown problem that can also happen in conventional CMOS circuit. Because in each write operation, we have to apply a voltage over the MTG device, and this high voltage can trap some charges, in the insulation layer, and these charges trapped gradually can malfunction the MTG. That is the reason of the breakdown hazard. One, it can be caused by the constant high voltage stress that can cause the conductive path in oxide layer that causing the MTG malfunction. For this TDDB malfunction problem, it can be described by the Weber distribution. That is the very typical distribution used to characterize the reliability of semiconductor devices. And with this Weber distribution, we based on the measurements from STT-MRAM prototypes to get the very important parameters such like the T63% and the beta values. And with this extrapolated parameters, we can estimate the lifetime of a single MTG device. After we get the single cell TDDB endurance, just like shown in this table, as we increase the MTG write voltage from 1.18 to 1.81, the write cycles or the write endurance shrinks sharply by many orders of magnitude. And this is the single cell TDDB endurance modeling. With this model, we can extend to one cache line or the total cache array TDDB endurance with these formulas. And I will not go into the details for these formulas. If you are interested in the TDDB modeling, you can refer to our papers. And by building the TDDB reliability models, we try to investigate how we can improve the reliability to try to reduce the effect of the TDDB breakdown. Because the write voltage has very large impact on the TDDB effect. Can we try to adaptively apply the write voltage without only applying single voltage for the MTG access? So we try to find an acceptable trade-off between the write performance and reliability. This work is based on very interesting observation, is that we can observe in the lower right, the right bottom figure, and we define the critical write and non-critical write when we run different kinds of applications. For the critical write, it means when we access the cache to write a data, another following access is to read the data from the cache. Because the high write latency of STT-MRAM RAM, we have to finish the write operation. After that, we can deliver the data to CPU through the read operation. And this write operation is defined as the critical write because it stores the read operation and may degrade the cache access performance, and also may degrade the microprocessor execution performance. But by evaluate many kinds of benchmarks, we observe that the critical write only occupies a fraction of the total memory accesses. There are also a large fraction of non-critical writes. So our idea is that for this non-critical write, which has little impact on the performance, we can use a lower write voltage to reduce the TDDB effect. But for the critical writes, we have to apply a high voltage. So through applying different write voltages, we can find an acceptable trade-off between the write performance and the reliability. This is our experimental setup and some performance and lifetime comparisons. And we have 4 different schemes. The first one is we always write with the low write voltage, that is 1.18 volt. Another one is we always write with high write voltage, that is 1.4 volt. The third one is our previous proposed technique called DOA. And the last one is the DOA Pro, an improved version of the dynamic voltage optimization to mitigate the TDDB breakdown problem. Through these evaluations, we can clearly observe that our proposed DOA Pro techniques can meet an optimal trade-off between the STT-MRAM write performance and the lifetime. At the same time, the energy reduction compared to the always high write voltage case is also very significant. It means we can reduce the write energy effectively as well. The third direction is the low power design for the STT-MRAM. We noticed, we mentioned that the STT-MRAM is non-volatile, has very low leakage power, but unfortunately, it also suffers from high write energy and latency. In this case, we profiling some back 2006 benchmarks, and we can observe that only a little fraction of data on average are changed during the during the cache accesses. So we try to reduce the data writing back to the cache. We can save much more write energy because the write energy and the latency are very high for the STT-MRAM compared to the SRAM. But the problem is that how can we identify the unchanged bytes or the unchanged data, and how to track them without first read this data back? Because before our work, there are some other researchers, they proposed a technique that to reduce the data amount writing back to the cache. They have, before the writing back, they will read the original data from the cache and compared the data to be written with the original data. They only write back the changed base. But this read operation aggravate the write latency because the write latency is already long. But before you write, you have to read the data back again. And the write latency now becomes the original write latency plus the read latency. Then the write behavior will degrade the microprocessor performance more severely. In our work, we try to write the unchanged bytes without reading the original data back. To achieve this, we try to use a different coding scheme, and we try to identify 4 different scenarios. The first one is that the data block has all zeros within it. And another one is half of this block are zeros. Another half may be some other data. For the the case C, it has the upper half as data 1, and another half may have some other data, either 0 or 1. The last case, the case D, it has some random data pattern. And by classify the data block into 4 different cases, we can try to identify what kind of data are not changed. For example, if the original data is A and the data to be written back is also pattern A, in this case, we can just drop this data without writing back. But in this case, we only compare the code without comparing the original data. That's why we can eliminate the read operations from the cache. But another problem is that if we use the 64 byte as our cache line size, we need the 32-bit for the pattern code. The area overhead is more than 60%, more than 6%. This is a large overhead that may be unacceptable. To reduce the overhead further, we noticed that there some dominating patterns appear during the application running. It means that we need not record all the data patterns. We only need to select these dominating patterns and encode these patterns so that we can reduce the code area overhead. But what will be the dominating patterns? And we just identify these patterns from 2 perspectives. One is the occurrence frequency. If the pattern occurs more frequently than other patterns, and then this pattern will have a higher priority to be identified as the dominating pattern. But note that some occurring very frequently data pattern may not correspond to the energy saving pattern, because this pattern, if the occurring pattern that is very frequently is case D, in this case, we have to write all data back to the cache. We cannot save any data. We cannot save any energy. So we have to use another metric that is called the energy reduction. By combining this metric, energy reduction characterize how much energy can be saved with this kind of pattern. By combining these 2 metrics together, we can define the weight that to identify a pattern as dominating or not. This is the working principle of our proposed scheme. First of all, the cache line was it read from the lower level cache to the upper level. During this loading procedure, we can encode the data patterns with the cache line and record it into a table called the PCIT table. Then we attach the index of this table with the cache line into the upper level cache. After that, when the data is evicted from upper level cache and need to be written back to the lower level cache, the index will be used to read out the original data code. And then the new changed data has its own new code. These two codes will be compared. With this comparison, we can identify which bits should be written back to the lower level cache, and which bits they remain the same and cannot need not be written back. We can just simply drop them safely. So through this scheme, we can save a lot of write energy. We also have some further improvement. And in the previous slides, we just mentioned the static profiling. It means that we identify the dominating patterns offline. But considering the running applications may change dynamically on chip, we propose a dynamic profiling technique that can construct the PCIT table dynamically depending on the online profiling results. This is some experimental results. And with our proposed technique, we can achieve 3% speed up because we do not need the read original data operation and save the write latency. For the write energy, we can reduce 37% for the static profiling scheme and 21% for the dynamic profiling scheme compared to our baseline case. And we also evaluate the effectiveness of our scheme on multi-thread cases and on quad-core or multi-core processor case. Except for the code patterning to reduce the write energy, we also propose an adaptive 3T3 MTG memory cell design. And in this case, we also focus on the perpendicular MTG device. This is the MTG parameters we use in this research work. And before our work, there are some other cell structures have already been proposed. That is the 1T1 MTG cell. I also mentioned this cell structure in previous work. And this is 2D2 MTG cell. Obviously, this cell structure has larger area overhead compared to the 1T1 MTG. But it used the differential sensing scheme, and so that the sensing margin can be doubled. We can sense the data stored in the MTG much more quickly. And so it can achieve very high read speed. And in the right side of this slide, it is the sensing scheme for the 1T1 MTG cell. For the 2T2 MTG cell, we do not use this reference voltage. We can use the complementary structure of the 2D2 MTG cell and use the differential sensing to read out the data. But it has a much larger area overhead. In our scheme, we try to combine the benefits of the two previously mentioned cell structures. And in this figure, we can try to read out the data through different readout schemes. In this structure, we use 3 MTG to store 2-bit data. The data 0 will be read out, and the right 2 MTGs act as the RAP, or high resistance and low resistance parallel connection, to generate the reference voltage. And then we can use the conventional sensing scheme to read out the bit 0. But at the same time, the MTG1 and MTG2 themselves, they form the complementary cell structure that is similar to the 2D 2MTG case. So to read out this bit, we can use the differential sensing. Then the bit 1 readout speed will be much higher than the bit 0 read speed. But we have to pay attention to that only several states are valid for this 3T3MTG structure. We must make sure that the data stored in MTG1 and MTG2 are always complementary, so that we can use the differential sensing to read out bit 1. We select the 4 different states through the total 9 states as the valid states for our 3T3MTG cell structure. To validate the correctness of our 3T3MTG cell structure, we perform extensive simulations, and we can observe that in the first read stage, the read latency is a little longer. It is because we use the conventional sensing scheme to read. But at the second stage, we read bit 1, the read speed becomes much faster. We also evaluated the process variation impact on the sensing reliability. And this is the Monte Carlo simulations results for the first stage and second stage sensing. From the right side figure in this slide, we can observe that with the process variation, we can also sense out the data very reliably. Finish the design of a 3T3MTG cell structure, we can assemble these 3T3MTG cells into the memory array to construct the STT-MRAM chip. We also give the layout of 1T1MTG and 2T2MTG and 3T3MTG. For the 3T3MTG layout, we can use the shared source and drain contact technique to reduce the layout area of the 3T3MTG memory array structure. And this is some experimental evaluations. We evaluate the cache areas and the read performance, read energy, and the write energy. For the 2T2MTG structure, it is larger than the 1T1MTG by more than 100%. And it also is larger than the case of the 3T3MTG by about 50%. And through these extensive simulations, we can observe that the 3T3MTG cell structure can get an optimal trade-off among the read speed and area overhead. More importantly, we can set the 3D3 MTG in two different working modes. In the high-speed mode, we can only use the bit 0 in each cell to achieve the fast sensing speed. And if in some applications they require large capacity, then the memory memory array can work in large capacity mode, so that both two bits can be used in one cell structure. By switching between the different working modes, and we can adaptively accommodate different kinds of applications running on the computing system. And finally, I would like to introduce another work about the data migration policy. Consider the thermal effect on chip. As we mentioned before, there is a very interesting thermal property of MTG, that is, with the temperature, the write energy and latency drop dramatically, and read energy and latency, they almost remain the same. So we try to use this thermal property to achieve a low power design by proposing a new data migration policy. Before I introduce the migration policy, I would like to introduce some basics about the on-cache architecture design. Usually, we use the uniform cache architecture. It means that the lower level cache manifests the uniform access latency to the upper level cache. It means that for L1 cache, it accesses the data in L2, the same latency assumed, no matter where the data is stored in the lower level cache. But as the L2 cache becomes larger, we can try to optimize the cache access performance with the SNUCA or the static NUCA architecture. This is a non-uniform cache architecture. With the distance away from the upper level cache, the cache access latency becomes larger. But compared to the uniform cache access, for the cache banks that is near to the upper level cache, they can deliver the data much faster. And another one is called the dynamic NUCA. It is an improvement over the static NUCA. Because in static NUCA, the data is statically mapping to a fixed location in the lower level cache. But in the DNUCA, the data can be migrated dynamically based on the cache access behavior. The intensive accessed data can be migrated gradually to the location that is near to the upper level cache. But unfortunately, current NUCA architecture design only concerned the traditional SRAM structure, and they do not take full advantage of STT-MRAM's unique property. Now let's look at what unique properties we can take advantage of. This is the thermal distributions on some typical multi-core processors. They have very significant thermal gradient, as we mentioned before. And as shown in the bottom part in this slide, the cache banks can be split into different thermal regions, the hot region or the cold region. And in the hot region, we note that the write energy is reduced compared to the cold region, because in the hot region, the thermal stability of MTG reduces. We can switch the state of MTG much more easily. Using this property, we propose a different data migration policy. And in the hot region, because we can use the short write pulse to reduce the write energy, And in these banks, we use the normal NUCA architecture data migration policy, so that the read-intensive data can be migrated gradually to the location that is near to the core. But in the core region, we use a different kind of data migration policy to promote the right intensive data to be more easily to be migrated to the hot region, because only in the hot region, the right intensive data can obtain the right energy savings. As shown in this figure, we use two counters to try to make sure that the right intensive data can be migrated more quickly than the read intensive data in the core region, because we assign different data migration priority to write intensive data and read intensive data. And for the core region, there is also a boundary bank that is the nearest to the location of the hot region. In this boundary bank, we have a different migration policy. For example, if this bank was just evicted from the hot region, and when it is migrated to the hot region again, we try to migrate further in the hot region to avoid the ping pong effect. And this is some performance evaluations when use our proposed technique. We can improve the performance by 20%, 22%. And also on the multi-program cases, we can also improve the performance as well. The performance improvement is due to the right activities in the hot region, because more intensive data they are located in the hot region. We can use a shorter write pulse or shorter write latency to write this data, so that the write performance can be improved. At the same time, we can also achieve the write energy reduction from 13% up to 41% of energy savings. This is because that we allocate more write intensive data in the hot region. But in the hot region, we can use short write pulse, and the MTJ state can be switched much more easier, and also use less write energy. This write activities evaluation in the hot region validate our technique from another perspective. From this figure, we can observe clearly that our technique can make sure more write activities happen in the hot region. That also illustrate the reason why we can save the write energy. Now, lastly, I would like to overlook the future of MRAM. As the new emerging applications that like neuromorphic computing and big data computing, we require much more powerful computing platforms. And we also need emerging memory technologies and other semiconductor technologies combined with 3D integration to deliver more efficient and more powerful computing ability. And for the emerging spin memory devices, such like the spin orbit torque memory and STT-MRAM memory, even for the non-spin memory, these all emerging spintronic memory devices, they have superior benefits compared to the STT-MRAM. They can be used computing in memory architecture and neuromorphic computing architecture. But how to take advantages of these emerging spin memory devices in the new emerging applications? At the same time, consider the unit reliability requirements. Also, uh, have many big challenges that need to be resolved, that need to be dealt with. So the summary of my talk is that the STT-MRAM is a promising memory technology, and in the post-war era, but it also faces some unique challenges. The device characteristics, such as the thermal probability and application probability, they can be explored to enhance the reliability of STT-MRAM without degrading the performance or the power consumptions. Of course, there are many emerging applications and it requires new spin techniques. But this combination also opens new opportunities and requires new reliable and low power solutions for the more efficient non-volatile memory system design. Finally, I would like to thank all the members in my cadet laboratory and our collaborators and founding sponsors. Thank you for your attention. And if you have any questions, please ask me freely. Thanks.
Thank you very much, Professor Yuanqing. It was a very interesting talk. And now we're going to switch to the questions. Our first question is from Abdelhamon Gamal Mohamed Kabt. He is from the University of Rochester, and he wants to know, what do you think about the multi-layer cell STT-PMTG as a base for multi-bit memory cell?
Okay, thanks for your question. This is a very interesting question. And I remembered several years before when I attended a seminar that some people also talked about how to use the multi-level cell STT-MRAM to achieve larger storage capacity. This is a very promising idea, but unfortunately, the multi-level cell cannot be implemented in the real fabrication process, as far as I know. That's why you can notice that in the IEDM conference or the ISSCC conference, there are many MRAM prototypes released every year, but there are seldom multi-level cell debut in these conferences, because the MTG device, it requires very strict fabrication steps. Maybe if you add another MTG that is stacking on the original MTG device, the original physical phenomenon may disappear. That means you cannot simply assume that the two MTGs stacked together can achieve the multi-level cell structure. This may not be correct, because when you stack them together, some original physical phenomena may disappear, and you cannot store the data reliably in each of these cells. But I'm also open-minded to the new cell structures. Except for the multi-level cell structure that was proposed several years before, there are also some promising cell structures, just like what I mentioned in my slide, like the SOT device and STT-M cell device, and some emerging and screaming devices. But all these kinds of emerging devices are in their infant period and may have a long road to come into the real product. And currently, the most mature product, I think it is the STT-MRAM, because the companies like Everspin and Honeywell, and also some other semiconductor companies like TSMC and Samsung, they have already um, built the fabrication lines in their foundry. And so I think the mainstream memory device in the commercial applications will also be the STT-MRAM cell. But of course, it is the single cell structure instead of the multi-level cell structure. Okay.
Thank you very much. Let's switch for the next question from Walter Calienis. He's from the PUC Peru, and he says, thank you for your nice talk. Are you planning to study STT-MRAMs under harsh conditions to test their reliability, like in heavy ion gamma radiation environments?
This is a very good question. And as I mentioned in the preliminaries of STT-MRAM, because we store the data using the spin property of the electron instead of the charge property of electron. Um, Conventionally, the very high energy particles, they strike on the MOS device and cause the flip of the MOS transistor state. Uh, but this radiation problem uh, can be alleviated uh, effectively by the STT-MRAM, because we use the magnetism to store the data, and the spin cannot be changed very easily by the high energy particles. So usually the STT-MRAM can be used in the high radiation environment. In fact, this is a unique benefit or advantage of STT-MRAM. Um, in as far as I know, that the first usage of the STT-MRAM is in the satellite or the aircraft, because they are in a very high altitude and very easily to be attacked by the high energy particles. Compared to the conventional SRAM structure, the STT-MRAM is much more immune for the radiation uh, radiation effect. Okay, I hope my answer my talk can answer your solution your question. Okay.
Thank you very much. Our next question, actually, our two questions are from Jason Silveira. He is from IFRS Canoas. And he first thanks you for the talk. He wanted to know which tool do you use to obtain the STT-RAM circuit level parameters for system level analysis?
Yes, we in the past several years, we built a framework from the device level simulations to the architecture level simulations. In the device level, and I recommend you can visit a very famous device website called the Nano Hub. And in this website, there are many different kinds of device models that um, are calibrated with the real measurements of the prototypes. For example, in my work, I um, I used the MTG model developed by the Purdue University, and but in their model, they only capture the basic working mechanism of the MTG. I have to add the thermal effect into this model and calibrate the model with the real data measurements of the prototype. Then you can use your model into the circuit level simulations. And this model is usually written with the Verilog A language that can be supported in the commonly used EDA tools like Cadence Virtuoso and other similar simulation tools. Of course, you can also use HSpice for the circuit level simulation. And after this circuit level simulation, you can also resort to the memory array level simulators like NVSIM developed by the uh, Penn State University or the Cacti developed by the HP company. With these tools, we can get the memory array um, behaviors, access parameters based on the MTG device input. After that, we can feed this array level simulation results and feed them into the architecture simulators. And that's how I get the architecture level simulation results. I hope this flow can also help you for your own research. Okay, thank you.
Okay, and his second question is Jason from EFSC Canoas. Could your DRAM be replaced by STT-RAM or other NVM as off-chip memory, considering read-intense applications?
Um, yes, I think this is the very good viewpoint. And originally, the STT-MRAM was proposed to replace the on-chip SRAM as the cache memory. But I know that the commercial company like Everspin, they also released the commercial STT-MRAM product for the main memory usage because they can support the mainstream DDR protocols as for the DRAM memory. But the problem is that the STT-MRAM memory has very high cost, and with the same capacity, the STT-MRAM may cost several times compared to the DRAM product. And this is the bottleneck for the widespread usage of STT-MRAM as main memory. And currently, um, I think except for the DRAM price cannot very scalable in the ultra deep submicron technology node. Otherwise, and STT-MRAM may have little chance to replace DRAM from the cost perspective. Um, but from the technical perspective, STT-MRAM can really be a very good promising candidate for DRAM. But sometimes the technical advantages does not mean the technical advantage does not mean that it can be successful in the commercial applications, largely because of the high fabrication cost. That's why we spent much efforts in this field, try to improve the reliability and the yield of STT-MRAM to reduce the fabrication cost. Maybe someday in the future, and for some low power applications, and you can find the STT-MRAM main memory in the computing system.
Thank you very much. I have just one last final question. If someone wants to make a question, please. We have a few minutes only. My only question is on your three transistors, 3MTJ that you presented on the sensoring. How big are the PMOS transistors in comparison to other approaches?
For this one, usually we do not use the PMOS transistors. we use the NMOS transistors in our MTG structure, because usually the um, mobility, electron mobility, is much better than the Hall's mobility. So that's why the NMOS transistor can deliver larger current compared to the PMOS transistor. And in this case, uh, because for the advanced technology node, such like 1x nanometer, the write current is much smaller than the write current in the 45 or 32 nanometer technology node. In this case, the driving current requirement on the NMOS transistor will be shrinked significantly. That's why the integration density for the advanced technology node of STT-MRAM RAM becomes larger. But usually, the cell structure, the area of the cell structure is mostly determined by the MOS transistors, because we usually fabricate the MTG between the metal layers that is above the transistor structure. And the MTG itself is very small, sandwiched between the two metal layers. And so from the area perspective, the cell structure is largely determined by the NMOS transistor area. But it is expected that as the mature, uh, as the STT-MRAM fabrication becomes mature, it is possible to achieve the full F squared area that is like the area of DRAM.
Okay, thank you very much. I think we don't have any more questions. Let's switch back to Professor Ricardo Reis. He has some announcements to do. Thank you so much, Professor Yuanqing Cheng. Thank you so much.
Okay, thank you. Thank you as well.
There is still a question by Professor Bumpy.
Oh.
Oh, yes. In the last minute, Professor Bumpy from URGS, he is asking which companies may have in large production the STT-MRAM in the next years.
As far as I know, I think the TSMC and Samsung, they are two big players of the STT-MRAM production. These are the two largest. They are also the two largest foundries. And just look at the RSAC conferences each year, and usually they have every year they have new releases of their STT-MRAM prototypes. And for the STT-MRAM, there are also some semiconductor companies, but are fabless companies. They pay much attention to, just like the Qualcomm and ARM. Although they do not fabricate the STT-MRAM chips, but I believe that many of the demands for the foundries are from these semiconductor giants, because like Qualcomm, maybe they can use the STT-MRAM that can integrate into the mobile phones, because in the mobile phones they require very low power and long standby time. So the STT-MRAM may be used to replace the SRAM cache or even DRAM memory inside. For the ARM company, because it is also a mobile chip designer fabless company, so I think STT-MRAM can also attract ARM's attention because of it can be used in the mobile applications. At the same time, the STT-MRAM product can also be used into the hard drives, because usually we use the DRAM as the data buffer between the main memory and the hard disk. but the DRAM also not very power friendly, and is volatile. And if there is a power off, the data stored in the DRAM, which acts as the data buffer between the main memory and the hard disk, may lose the data. So I know that some company use the STT-MRAM as the data buffer between the main memory and the hard disk to take advantage of its low power and non-volatility characteristics. Okay. Thank you for your question.
Okay, thank you. I would like to kindly ask if you have more questions to send an email to Professor Yuanqing Cheng. And thank you so much again for your talk. Please let's switch back to Ricardo Reis.
Okay, so thank you very much, Carolina, to be the session chair of Yuanqing Cheng talks of today. So thank you again, Yuanqing Cheng, for your very nice, inspiring talk.
Okay, thank you.
So,
Thank you.